Now, another important thing is the rolling motion. Rolling motion. Something is, on the one hand, it is turning, on the other hand, it is moving. So, at the beginning of the chapter, remember we said that the rotations were around the fixed axis. For instance, if let's again make use of our famous wheel. So far, or in the first two lectures on rotational dynamics 1 and 2, we had generally a rotation around the fixed axis. This axis was staying in the same place. It wasn't moving to a new position. However, now rolling is real, riding a bicycle, for instance. A car is moving. So this wheel is not just turning around the fixed axis, the axis is also moving, just like a normal car, bus, bicycle, whatever, is moving. So you are riding a bicycle and that bicycle is moving. So rolling is a combination of two motions. One is pure translation, the other is pure rotation. So that, for instance, let's say this is just a wheel. So that, let me have a reference. So AB, for instance, AB is a diameter, and this object is moving without any rotation. It is just sliding without any rotation. This is called pure translation. Pure translation. So AB is always in the same vertical position. Pure translation. Now the second thing is pure rotation. So this is the object. So AB now becomes AB, then AB, then AB. So it is turning. This is called pure rotation. If you add them up, you get the rolling motion. If you add pure translation and pure rotation, you get the rolling motion. So in other words, rolling is pure translation plus pure rotation. In the first case, there is no rotation, it is just sliding without any change in the orientation. In the second, it is just turning around the fixed axis but without moving anywhere else. If you add them up, you have the real motion where you are riding a bicycle, so you turn the wheels on the one hand, but you are also moving along the x-axis. And let's now compare the velocity vectors for this motion. Now let us compare the velocity vectors. For instance, for any case, assume this is the object, the wheel, and it is moving. On the one hand, if it is just moving in this case, it has some velocity vectors along the different points of the diameter. This is the center, let me show it by letter O. So this object has the same linear velocity vector, V. Let me call it V0 for instance. V0. V0 is this velocity of the center of mass, but also every other point is also moving at the same speed if you have just pure translation. On the other hand, for pure rotation, this is pure translation. For the case of pure rotation, since it is turning around the center O has no speed. But as you go upward, according to the relationship V is equal to omega times R, so we have here sort of such a triangle. So these uppermost and lowermost points have opposite speed, minus V0, plus V0. This is something less than that, something less than that. Nothing here to the left, and these are equal and opposite. Those are equal and opposite. So this is the case for the pure rotation. We take into account only one diameter and see the velocity, linear velocity vectors. Of course, this is turning by this omega, and this is moving by some linear speed. Now, in the case of rolling, which is the combination of these two, what happens to the velocities of different points along a vertical diameter? In this case of rolling, because this corresponds to pure translation, that corresponds to pure rotation. Now, what about the rolling case? So we add up the velocity vectors for each point. So this is the circle wheel, for instance. Let me draw this a bit better. Alright, now for the central point, let's start with the center. There is nothing here but a V0 there, so there's only one V0 for the center. Alright, what about the highest point, uppermost? In this case, we have one V0 to the right because of rotation, one V0 because of translation. So we have two V0 for the uppermost position. And then we have another sort of triangle. So this one is plus 1 V0, that one is 2 V0, but other intermediate points have accordingly other values between 0 and that. So here we have, for instance, one vector to the left and one vector to the right, and they cancel each other exactly. So the lowest position here, let me call it VP, because the books generally call it VP, the point. Which point? It is the point, lowest point of the wheel that touches the ground. So this VP is taken to be 0 in cases of rolling without friction, as I will explain. So this is the general velocity profile for a wheel turning and rolling on the ground. It is on the one hand turning clockwise sense and also moving at the speed of V0. And omega, for instance, is just V0 over R. On the one hand, it is turning at an omega, which is V0 over the radius, but on the other hand, moving as a whole with a linear velocity V0. So this is called rolling motion. And these are the velocities. It may come at the beginning, at first sight, it may come as a surprise that this point doesn't have a velocity. Because continuously, this point is changing. As the object is turning in the clockwise sense or counterclockwise sense, without any relative sliding between the ground and the wheel, so this point is the one which is the lowest. A bit later, delta t later, so a new point will come here, and that will be the new lowest point. And a bit later, a new point will take the place of the lowest position, etc. So that point does not have any horizontal speed. And center has only V0, and uppermost position has twice V0. And in the case of rolling without friction, different cases. Let me compare 3 cases. Now let's compare 3 different possibilities for this rolling motion. And draw some smaller circles, unfortunately, because of lack of space. Let me draw this disk in a smaller way. So the object is moving. In all cases, this disk is moving to the right. On the one hand, it is turning. On the other hand, it is moving. But there are slight differences. Let's say in the first one we have so for instance AB. In the second one, let's say it is moving less than that, with a smaller angular speed. But these positions are corresponding. So this distance, let's say, is x. In every case, the distance covered is x, the same distance. So let's look at it that way. And in the third one, we have, beginning initial states are the same, but then it is turning too fast. So if you compare the three cases of interest, all of them, in all cases, the object is moving from left to right and covers the equal distance of x, x, x. However, in the first case, there is a certain angular speed, but this x is now, let's say, 2 pi r, because pi r, half, pi times r. Because at the beginning, let's say as a reference position, this is the initial position, it is turning and completing a half turn. So half a turn is just half of the circumference, which is not 2 pi r, but 1 pi r. So this distance is just equal to 1 times pi r, for instance. In the second case, it doesn't cover that much distance, or x is, let's say, x is greater than pi r in this case. This one is, it doesn't finish half a circle. In the third one, it finishes more than half a circle. It completes one full turn, so that in the case of the first case, it is called the first one, the first one, 1, 2, and 3. Let me call them 1, 2, and 3. In number 1, the first one is called rolling without friction. 1 is called rolling without friction, where x is equal to, let's say, pi times r. Or, for example, let's consider it the other way. Let me draw a smaller disk. Alright? So if it starts with AB like this, and after some rotations, and it comes to AB again, it comes back to the initial position, then this corresponds to one full turn, And on the other hand, the distance covered is x, so that x, that the center of mass covers, if x is equal to 2 pi r, then it is called rolling without friction. But, for example, sometimes you try to drive in a muddy surface or on an icy road. In those cases, you push on the accelerator pedal. However, the wheels are turning, maybe too fast, sliding, but the car is not going as required. So, for example, here in the middle case, in the last case, sorry, in case 3, for example, it is turning too fast around the center of mass. However, it doesn't go as required. So this number of turns is more than the horizontal distance corresponding to the motion of the center of mass. In number 2, for instance, it doesn't turn that much, so that the distance, it is sliding. Yeah, it is not turning as rotationally, it doesn't turn sufficiently, but the object is sliding as a whole. Only in the first one where the distance covered can be related with the turn. For example, if it starts from this position, if let's choose a reference for the diameter, it is turning and coming back to the initial vertical position. During these 2 points, the distance covered is just 1 full turn, and also it is 2 pi. If it is this condition, x equals 2 pi r, then it is called rolling without friction. And in those cases, make sure that you can take v is equal to omega times r. Otherwise, v is not always omega times r. If you do not read the label rolling without friction, then please have some doubt on writing v is equal to omega r. If you read necessarily, for sure, if you read rolling without friction, then v is equal to omega r can be applied. Now let's have another example, which is familiar to us. Again, we are familiar with it. It is a kind of conservation of energy principle, but this time the object has a second kind of energy. Now let's say we don't have a block. Remember, maybe you immediately recognize the problem. In the previous chapters, we had such a, in the energy conservation of energy chapter, we had this example, but in that case, there was a block on the inclined plane. And at the end of the inclined plane, there was it is called the loop-to-loop road, so that this block was sliding without any rotation. Of course, it was a block. It was sliding down and turning here and reaching the uppermost position, etc. So we tried to find the normal force acting on the particle at the lowest position, at maybe horizontal position, at the top. And also we were solving for the minimum height, because this is the starting from a certain height, h from ground, etc. There was a block. And here we have the same problem, except that we have something which is rolling. That's rotating object, rolling object, maybe a disk again, maybe a wheel, maybe a sphere, a spherical shell which is empty inside, or a full solid sphere. Assume it's a solid sphere. And it has a bit different inertia. That's the only difference. Otherwise, the ideas are the same. A solid sphere of mass m, solid sphere of mass m, little m, radius r, little m, little r, radius r, starts to move down, to roll down an inclined plane from a height h. At the end of the plane, let's call this point A initially, from a height h, point A. At point B, it starts to turn up in a circle. At point B, it starts to turn up in a circle of radius capital R. There are two R's, little r and capital R. Radius capital R, and if you compare them, this R is much less than R. It is also given to make it simpler for the calculations. Okay, this is the idea. This R is, let's say, let me draw it in a smaller way. So this object is as a radius R, that R is much less than the radius of the road. Alright, find find the normal force F at point B, for instance. B at point B. Find the normal force F, FB at point B, FC at point C. C is the, by the way, uppermost position. This is C, that is B. So this is perpendicular. And then let's add a part C, because in that problem previously we had found the minimum height h where we should leave it, release the object so that it completes the circle and it can reach point C. What is the minimum value of height h? Or find the minimum value of height h. Find the minimum value of height h such that it can pass by C, such that it can reach the sphere, the ball or the sphere can reach point C. So this much was already familiar because we have solved it. However, let me repeat the difference. The only difference between those two cases, between the previous one and this one, is that this object is now turning. However, in the previous one we had a block which was just sliding. So it had only linear kinetic energy. This one has both linear kinetic energy of the center of mass and the rotational kinetic energy around the center of mass. And also the problem gives you the value for the I for the solid sphere. It is 2/5 mr squared. It is not 1/2 as in the case of disk cylinder, but 2/5. If you've got an empty ball, spherical ball, which is empty inside, it would be 2/3. Alright. Now this is the text of the problem. Now we start with part A. So we will compare A and B. First part says find the normal force Fb at A. So we should find the velocity of the object at B. We should find the velocity Vb at point B. But in order to find it, we should write not only the energy conservation but also the forces. For energy conservation, energy EA is equal to energy EB, as we did several times before. EA and EB. And again, let's, for simplicity, we can choose this level to be 0 level, so that initially it had a potential energy, so that potential at A, kinetic at A, potential at B, kinetic at B is the idea. So initially there is mgA, mgh, yes, m times g times h, but nothing as kinetic energy because it is at rest, it doesn't rotate yet. Plus a 0. Now, in the case of, or at point B, it has no potential energy because we have chosen this level to be 0 level. But it has two kinds of kinetic energy. One, linear, the other rotation. Linear one is 1/2 m times Vb squared. And don't forget the additional one, angular one, 1/2 I omega b squared. 1/2 I omega b squared. What is omega? Omega is given. I is given, omega is Vb over R. So that omega b is just Vb over R, which R, of course, it is the radius of the rotating object, little r. Little r. Please don't confuse it with capital R. Capital R is just the radius of the road, which has nothing to do with the relationship between the velocities of the ball. So we will place, substitute omega b here, and I is also substituted from above. So we have, let's write 1/2 m Vb squared plus 1/2 m 2/5 m r squared multiplied by Vb squared over r squared. So these r squares will cancel. Those m's, this is equal to mgh. The other side is mgh. mgh. So m's also now will cancel. So that we have Vb squared multiplied by, these twos also will cancel, 1/2 plus 1/5. 1/2 plus 1/5 is equal to just gh. This is 7/10. So this is just 7/10. Therefore, Vb squared, we don't have to take the root anyway, we'll use Vb squared in the force equation. Vb squared is just 10/7 gh. So we found the velocity, but in order to get to the forces, we should write the force equation. At point B, what are the forces? So this is point B. Here is the object. What are the forces acting on it? There is a force of mg acting down, and a force of normal force, which is normal at point B. We do not draw any such thing as mv squared over r. Of course, mv squared over r is pointing towards the center, never outside, as I said several times beforehand. So the difference nb minus mg is equal to the net force of, in this direction, which is mvb squared over, now of course this is the radius of the road, which is capital R. And nb is what we have to write, and vb squared is simply placed from this previous finding. So that nb, normal force as it passes by point B, is mg, take it to the right as positive, plus m over r multiplied by Vb squared, which is this 10/7 gh. Alright, so let's write it in a more compact way. Nb is just mg multiplied by 1 plus 10/7 h over r. 10/7 h over r. So this is the quantity. As you see, of course, it is something greater than the weight. For someone who thinks that normal force is just mg, I suggest him her to look at this result. NB is necessarily greater than the weight of the object. Otherwise, it wouldn't curl up. It would just move straight away. But the rho doesn't let the particle to move straight. The force should apply a force greater than the weight of it, so that it starts to curl up. At point C at the top, assume that it reaches there. Part B, assuming it reaches point C. Assuming it reaches point C. It reaches and passes by point C, so that it is still in contact with the road as it passes by point C. Then, from energy conservation, we can compare, for instance, energy at the beginning and energy at the top. EA, first we have to write EA is equal to EC. What is EA? It is just mgh. What is EC? It is, first we have some potential energy, mg times 2r, m times g times 2r, and it has 1/2 m. But it is not only V, it is V sub C, because VB, VC, VA are all different. Don't forget to put this index, VC squared, but also 1/2 I omega C squared. Now we continue, and there are some cancellations, of course. MGH is equal to, let's say take 2R here, mg times h minus 2r on the one hand equals 1/2 mvc squared plus 1/2 2/5 mr squared vc squared over r squared. There are some cancellations. First of all, these 2's will cancel, m's will cancel throughout, those r squares will cancel. So we have, for instance, VC squared again, VC squared multiplied by 1/2 plus 1/5 again equals G times H minus 2R. So when the object is coming here, turning, and then passes by this uppermost position, again this is 7/10, VC squared times 7/10 is equal to G times H minus 2R. So VC squared is simply 10/7 G H minus 2R. But what about the forces? Now the forces are, as it passes by point C. This is the object, and the forces are both downward, because normal force is applied by the road, by the inside of the road, so it is downward, and also the weight mg is acting down. So some of them should supply the necessary force to rotate in a circle, because some is also acting towards the center. As it passes through the inside of this road, the forces are downward, so that it is the sum nc and mg, which is m times v, but vc. Please be careful. Point B, point C are all different. Vc squared over the radius r. We don't write r minus r here because the problem says that radius of the particle is much smaller than the radius of the road. So it is just enough to write it as capital R. We don't have to subtract little r from it. Alright, so we want to find nc. Therefore, n sub c is equal to m times vc squared over r minus the g. Alright, nc is just m vc squared over r. Vc squared is here. So this VC squared will be placed here. Alright? So M times VC squared over R. VC squared is 10 over 7 G times H minus 2R whole thing over R minus only G. So we can take this G outside. Let's complete here. M times G multiplied by 10 over 7. G is already written. We have H over R minus 2, but minus 1 also. This one. So we have mg. If you multiply that, you get 10h over 7r minus 20 over 7 minus 1. mg 10h over 7r minus 27 over 7. Okay? 20 over 7, 7 over 7 minus 27 over 7. And this is the result for the normal force at point C. So this is a number, unitless number, because distances cancel. This is also a number, so pure number times the weight mg. So NC is a force. And the critical point is now the last part. What is the minimum value of height h so that it can reach and pass by C without losing contact with the road? Part C. In order to pass by point C and not to lose contact, in order to pass by point C and not to lose contact with the road, normal force should at least be 0. Normal force cannot be negative. The object should move only by its weight. By its weight mg. So that and C should be 0 there. Just a loss of contact with the ground, road, and the object. If NC is 0, go back to part B. If NC is 0, mg cannot be 0, so it is the parentheses which should be 0. So that 10h over 7r has to be 27 over 7. So 7's cancel, and h turns out to be 27 over 10 r. In other words, h is 2.7 r. However, if you remember the previous problem where we had a block sliding down, comment, in the case of block, right? In the case of block, h turned out to be, remember, 5 over 2r or 2.5r. But this time we don't have a sliding block, we have something which is rolling down. So that h has to be a bit higher. It is expected to be a bit higher than the previous h because it has to give some part of the energy to the rotation part. So necessarily it has to start with a higher position, at a higher position from the ground than the previous case of sliding block. If it were, for example, if it were a disc, for instance, not a sphere, because sphere, remember, isolated sphere is 2 over 5 mr squared. But if it, for a disc, it is 1/2 is less than 2.5, 1/2 is less than 2 over 5. it is 1/2 mr squared. This distance would be, for this h minimum would be 2.75 r. Here it is 2.7 r. But in all cases, if the object is something which is rolling down, the initial height should be a bit greater than just the sliding objects. Because some part of the initial energy should be allocated to the rotational kinetic energy. This is something expected. Depending on the case, on the object rolling, whether it's a solid sphere or an empty sphere, spherical shell, or a rod or a disc, whatever, this initial height changes slightly, but it is in all cases greater than 2.5 r, where we had a block sliding down without any rotation. Now let's consider a problem from the book. As an example. A ball, this time it's an empty ball, a ball of mass m, radius r, starts from rest at point A at a height h from the ground. By rolling down, it gets velocity. By rolling down, it gets some speed on the rugged part, coarse part. This is not very smooth. On the rugged part, then after point C, point B, it enters the smooth part. At point C, at point B, it enters the smooth part. And reaches point C at the height h prime. At the height h prime. Find h prime in terms of h. Find h prime in terms of the initial height h is the problem. So what is the physical idea in such a problem? And what is the difference between the rugged part and the smooth part? Of course, as we understand from the text, the ball starts from A, rolls down, so it gets, of course, a linear speed by the center of mass, and also has some angular speed here. Reaches point B. But after that, since it is moving on a smooth part, when it reaches the new maximum height, point C, at a different, possibly different height, h prime, and h prime is expected to be less than h. Here, when it reaches here, its angular speed during the whole motion remains the same. So we understand from the text that if it is moving on a smooth surface, its linear speed is changing, of course, because it is rising up. Its linear velocity of the center of mass will get less and less, just like some block moving up. But on the other hand, its angular speed remains the same as in part point P. So for example, we understand that omega C will be omega B. However, VC, but VC will be 0. So we understand that. VC is 0 because this is the highest position it can climb on the smooth part. But on the other hand, since it is moving on the smooth part, it doesn't lose any angular velocity. So omega C at the top position is the same as the beginning point of that smooth part, which is point B. So first we equate the energies between A and B, so we find the velocity at B, and then use the same velocity for the rotational part only at point C. So we have, for instance, energy at A is equal to energy at B. And initially, that, as we do in all cases, let capital M, G, and H with respect to this 0 position is the potential energy at the beginning, plus no rotational, no linear speed, equals, when it reaches here, it doesn't have potential, but it has two kinds of kinetic energy. 1/2 capital M VB squared plus 1/2 I omega B squared, and we know that omega B is simply VB over R. So it is easy to find. MGH is 1/2 M times VB squared plus 1/2 another, what is this? It's a ball. It's a ball. I is equal to 2/3 M times R squared. This is also given by the problem. It's an empty, as I said before, for an empty ball, the inertia is greater than that of a solid ball. So 1/2 times inertia, which is 2/3 M times R squared multiplied by VB squared over radius squared. So there are some cancellations. First of all, we cancel through the M's, and then these 2's will be eliminated, and also these R squares. So we have, after VB squared, we have 1/2 plus 1/3. On the other side, we have G times H. So this is 5/6. VB squared times 5/6 is GH. So we understand that VB squared is simply 6/5 GH. And as we have assumed here, it's omega, which is this quantity by R squared, will remain the same throughout the second part of the motion on the smooth road. So that energy at B and energy at C. Energy at B is simply energy at A. So we can simply use this case where MGH can be taken. So M times GH can be taken. On the other side, we have potential energy here. So we have potential energy, capital M, G, and H prime, which is unknown. H prime is the thing we have to find. MGH prime plus no linear kinetic energy because the center of mass of the ball stops, but there is still some angular kinetic energy, which is 1/2 I omega C squared. And I omega C and omega B are the same. So omega C is omega B, which is VB over R. What is VB? VB squared over R. Omega C squared, omega B squared, VB squared over R squared. What is VB squared? It is just this thing. So we write it here. So we write it there as 6/5 GH. So we continue with this expression, MGH on the left hand side, MGH on the left hand side, MGH prime plus 0 for the linear one, 0 for the linear one, 1/2 I. What is I? 2/3 m r squared times omega c squared. But omega c squared is just this quantity over r squared. So we have 6/5 gh over r squared, and we only have r squares cancelling. Also, as usual, m's cancel, 2's cancel. So we have gh on the left, gh prime on the right, plus what is remaining? 6/3/5. 6 and 3 also by this becomes 2. 2/5 gh. As we see, g is also cancelled. So we have h prime is equal to h minus 2/5h. So it is h prime is 3/5h. 60% of the initial height. It can reach only 60% of the initial height because of this difference in the two parts of the road. In this part, we arrive at the last part of the rotational dynamics, which is maybe the most important part, angular momentum. We have seen before in chapter 8 the linear momentum. And we define the linear momentum as the product of the mass of the object and the velocity if it is moving. So the linear momentum of an object, it was generally defined by P. Momentum was defined as P is equal to mass of the object times the velocity. For example, if we have a road and a car moving, car of mass and moving at velocity v0, it has a certain linear momentum, mass m times velocity v0. If numbers are given, it's kilogram times meters per second. So the unit of P, for instance, was kilogram meter per second for the linear momentum. And immediately we used it in case of collisions. Elastic type, inelastic type. If energy is lost but only momentum is conserved, it was, remember, an inelastic case. If both energy and momentum are conserved, it is called elastic collision, etc. But we had an equation. Remember Newton's second law. Newton's second law was first seen in the first chapters as mass times acceleration. But when we come to this chapter, linear momentum, we modified it, or we looked at it in a bit different way. Then it becomes what? dP by dt, or let's say delta P by delta T. And let's write that P2 minus P1 over T2 minus T1, or time interval where this change occurs. And you can find in the previous lectures on linear momentum, in one of the lectures, you can find what is told here. So there is no need anymore to go on these same topics again. But I will just compare the corresponding thing, because from the beginning of this rotational dynamics, I've been comparing the linear quantities with the rotational ones. So please try to understand angular momentum in the same way. So in the linear motion, if something is moving on a road, something having a mass m, so many kilograms, and moving at a certain velocity at so many meters per second, for instance, then we simply multiply them and get the linear velocity, the linear momentum P. And what is the related equation? It is easy to find P, but more important thing is what happens later on, because this object is not keeping or doesn't keep moving at the same speed forever. It will do something else. Maybe the velocity will change, maybe some force will act on it, maybe some positive force will act on it to increase the velocity, maybe an opposing force, braking force will act on it to slow it down, so that again it has an acceleration, but it has a deceleration now, negative. Or it will hit a second object, make a collision, elastically or inelastically, and what happens at the end of this event if they join and become a single part, single object, a combination, then momentum is conserved, some energy is lost, so energy is not conserved, and we are generally interested in the final velocity of this combination. But please try to see this through this point of view, because force is not just m times a. This is not the only one way of writing it. Change in the momentum during a certain time interval. We have also seen the impulse, concept of impulse, J. Please, if you forget some of them, please, I refer the previous videos, lectures on linear momentum, impulse, and collisions. Alright, you can go back and refresh your memory on these topics. So delta V by delta T, if there is any change in the momentum, then necessarily some force is acting on it, or vice versa. If a force is acting, it means its momentum is changing, maybe increasing, maybe decreasing. But we have also said that every quantity in the linear motion corresponds to an angular quantity in rotational motion. And we started with, remember the table for instance, we started with distance covered and angle theta. At the end we arrived at the force and torque. Previously force corresponds to torque. Now we have linear momentum, angular momentum. So linear momentum is P in the linear motion, and now we have capital L. Here capital L is not the distance, it's not the length of an object. Capital L, so I avoid using length L in cases where you may have some trouble. I use little b, lowercase b for the length of an object in cases where one can have difficulty. So capital L is the angular momentum. And what do you expect for the equivalent part? So P is equal to mv. So P equals m times v in the linear case. So L is the quantity for angular motion. So what is the linear one? M. What is it equal to? What does it correspond to? Inertia, rotational inertia I. And this one is corresponding to angular speed omega. So instead of P equals mv, we have now L equals I times omega. Angular momentum, in other words, angular momentum is just moment of inertia times angular acceleration. Angular velocity, sorry, angular acceleration is torque. Angular velocity. So units are kilogram meter square from this, and this one is some radians per second. So again, a whole combination of units. It doesn't have a shorthand unit L. So this L is a vector quantity. First of all, I will say that L, angular momentum, is a vector quantity. It has a direction. The angular momentum, the angular velocity, omega is written as omega with a vector. So the angular momentum L is also written with a vector. What is the direction of that vector? How did we define omega in the previous lectures? If something is turning, you grasp the object by your right hand, curl your right hand fingers in the sense of rotation of that object, a disc for instance, and your thumb, which is perpendicular to that plane, shows you the omega. Similarly, L points in the same sense, except that if you multiply omega by this rotational inertia I, you get the magnitude of L. So L may be longer than in vector notation. L may be a longer vector than omega because of this multiplication. Otherwise, in some cases they are not pointing in the same sense, but for the scope of Physics 101, we are interested in the cases where both L and omega point in the same sense, parallel vectors. So L, in these cases, vector L is vector parallel to vector omega in general. Of course, there are other cases where they do not point in parallel, but they are outside the scope of Physics 101. We also have, remember, F is equal to delta P by delta T, as I said before. But now we have, what is the corresponding thing for F? It is torque in the angular motion. Therefore, it is delta of L by delta T, change in angular momentum. So, what is the physical meaning of this upper line? If a force F is acting by a time delta T, the physical interpretation, explanation is the following. If a force F is acting on the system, on the object, by a time interval delta T, then its momentum will change by delta P. So this is the interpretation of the upper equation. In other words, F equals m times A. In the new case, we have torque for F, L for P. So that we have now torque is equal to delta L by delta. What is the interpretation here? If a torque is acting by a time delta T, then its angular momentum will change. Change means maybe an increase, maybe a decrease. Will change by delta. So the same, almost the same idea, except now we have some rotations. But again, go back to the previous topics, linear momentum. If F external were 0, then delta P would be 0. In the linear case, if F external, remember this is external, this torque is also external. External means from outside. So if F external is 0, then the right hand side is 0. That right hand side 0 means delta P is 0. Then delta P is 0, but delta P is P2 minus P1. So that there is no change between the initial and final linear momentum. And in most cases, we were dealing with such problems where there is no external force acting on the system from outside. Only the elements of the system were exchanging forces. For instance, there was a boat and a person. As the person walks by pushing the ground by his feet backward, so the center of mass was remaining the same, in the same position, so that as the person was moving in the negative x direction, boat was moving in the positive x direction, and vice versa. And there was no external agent doing work on the system from outside. And in this part, in this chapter, in this section, again we are rather interested in those cases, because this equation can be interpreted as if tau external is 0, if there is no external torque acting on the system to rotate it or to slow the rotation, if this is 0, then delta L is 0, but delta L means L1, L2, they are the same, or L initial equals L final. Conservation of angular momentum. This is conservation of linear momentum. So in case of no external force, we had conservation of linear momentum. Here we have conservation of angular momentum. Conservation of angular momentum. Let's, for instance, consider a simple example on this. But first, let me show the directions before that. So, for example, if this is the disk turning around this axis, for instance, this object is turning this way, then using the right-hand rule, remember, using the right-hand rule, this object is turning that way, so the thumb gives us the omega vector, which is pointing perpendicular to the disk. And if it is turning the other way, for instance, let me show it in a different way. For example, if this is the sense of rotation, omega, then this omega vector shows the omega vector for this rotation perpendicular to the surface of the disk. What about the direction of L, angular momentum? Since it is L is simply I times omega. Of course, it is not as simple as this. In general, in more advanced texts, for example, in classical mechanics, we are dealing with not just a single I, but with a 3x3 matrix, inertia tensor, etc. But for Physics 101, we exclude those relatively more difficult cases and consider I as a single number, and L is just linearly proportional, directly proportional to the angular velocity vector. So let me draw another vector here and something maybe longer. Let's say this is the L vector, and they are parallel. This is also an L vector, which is also parallel to omega. So they are again side by side. Now consider a collision, and try to solve this in a case where linear angular momentum is conserved. For example, before we solve some problems, let's consider some relatively simpler things. L, L1, L2, L3, angular momentum is conserved means the following. If angular momentum is conserved, if angular momentum is conserved, which means L1 equals L2 equals Ln, for instance. For instance, we are rotating on an icy surface, like the ice skating, for example. Someone is turning on the ice, but there is no external torque acting on it, frictionless ice. So there is an initial omega, and then by changing I, omega can be changed. Since this is, for example, I1 omega 1, I2 omega 2, In omega n. So by changing I, one can change omega. For example, if you have a turning chair, right? Yeah, this is a, let's say this is a disc, for instance, but that disc can rotate clockwise, counterclockwise, and you are standing on top of it. Okay, so you hold two dumbbells, for instance, okay, and you are turning with some omega 1. For instance, you are standing on a turntable, right? And you hold two dumbbells, little and turning, or some friend is turning you. So you have a certain, for instance, I1. I1 consists of your body and your arms with the dumbbells. Alright? So you are turning with omega 1. What is I1? It is just I1 times omega 1. Can you change I1? Yes, to some extent. Because your body is again there, so you just like a rod, for instance. So a rod is a cylinder. This is almost a cylinder. A cylinder is turning around itself, 1/2 mr squared. But also, you cannot change your body's mass or radius in such a small time, but you can change one other thing, which is the additional part. So instead of holding your hands stretched, you can maybe stand like this, so that you are turning as a longer rod. So for instance, in the second case, let's say this is the object and this is your head, but you are holding these dumbbells like this. So in this case, as you see, the radius, this is the longer radius, but the radius now is smaller, much smaller than the previous case. So we have I2, but I2 is less than I1, so that omega 2 is greater than omega 1. So you can increase your speed, angular speed, by playing with your rotational inertia. If you increase or decrease it, you can decrease or increase, or conversely, your angular velocity around this vertical axis. So there's no external agent acting on you or any part of the system. The system is you plus the dumbbells. There's no external torque. But by changing one part, decreasing I, you can increase omega, or vice versa. So this is how angular momentum is conserved. The product is conserved. Maybe here, for instance, you can compare 16 times 2 is 32, but if you double this one and but cut in half the other one, 8 times 4, it is also 32. So the products are 32, however, as you increase the first part, or as you decrease the first part, second part increases by the same ratio. This is the conservation principle. You have a product, one thing, times something else, and by changing one of them, for instance, you decrease the radius, so that by decreasing the radius of your arms, because remember that I was what? Mass times distance squared. These small masses, dumbbells, were initially at a distance, let's say r from your body, so m times r squared, m times r squared. But then by holding them stretched up, you have almost no radius. So initially, we have only I0, your unavoidable, non-reducible quantity for the inertia, plus the I dumbbells. In the second case, this was the initial. In the second case, you only have I0, but dumbbells do not give any other contribution. So your inertia has decreased somewhat. Therefore, accordingly, your angular speed should increase by the same ratio. This is the conservation of angular momentum. Now let's consider a collision. In this case, a bullet is coming and hitting a rod, which can turn around its midpoint or one of the endpoints, etc. But this is happening on a frictionless horizontal surface. So this is on a, first of all, you should imagine that this is a plane where a rod is placed and some bullet is coming, let's say this way, and then it will be stuck in it, and the system turns around the midpoint This is fixed, by the way. This is fixed. It cannot be, it doesn't have to be fixed, as we will see in the following cases. Let me write the text first. A rod of mass m, length b, is placed on a horizontal frictionless ice. On horizontal frictionless ice, and it can turn around its center of mass at O. So O is this point. So it can rotate around this center of mass position, but doesn't go anywhere. It is fixed there. It can turn around its center of mass fixed at O. Fixed at point O. Then a bullet of mass little m moving with velocity v0, moving with velocity v0, hits it at one end and remains inside. Part A. Find the angular velocity omega of the system rod plus bullet after the collision. Part B. What would omega be if the rod could rotate around the other end? And see write the equations for the motions if the rod were not limited to stay at the initial position. So let us look down the system. So we have the top view is the following. The top view. Here is the rod, and it is fixed at the midpoint, so it can rotate but doesn't move on the surface. All right, the bullet is coming towards it with a velocity v0. And after that, yeah, it becomes embedded in it, stay inside, so the system turns out turns around the initial position, the central position by some omega. And we want to find that omega. So what is the idea here? The physical idea is here is tau is equal to delta L by delta T will be used, and it means there is no torque acting on the system, because bullet is not something external. Bullet and rod together is the system. If you isolate the system from environment, it is rod plus bullet. So our system, rod plus bullet, has the same angular momentum throughout this motion, collision. So let's consider part A. There is no external torque on the system rod plus bullet. Then how do we write the equations? The bullet has initially some linear momentum. The bullet has initially means just before collision. The bullet has initially some angular, some linear velocity, some linear momentum, P initial, mass times V0. Because linear momentum is mass times velocity. And we also have an equation R cross P. L is equal to R cross P. So L magnitude is R times momentum M times V times sine of the angle in between, sine theta. But R is, in this case, let me draw the picture again. So this is the rod, and that is the vector R from the center to the point where the bullet will hit. But this one, P is such a vector because the bullet is coming this way, perpendicularly. So there is angle 90 degrees. And R cross P, if you are interested also in the direction of that L, it is R cross P. So R cross P is something, R cross P is out of the board, out of the page. But this is not in question now. Therefore, L is simply distance R. What is the distance? It is half of the rod's length, B over 2. So distance R is B over 2. Multiplied by the linear momentum, little m for the mass of the bullet, velocity V0, and sine 90, which is 1. So this is the initial angular momentum just before collision. Next, just after collision, what is L final? L final now is written as I times omega. Rotational inertia times the angular velocity. It is I final omega. What is I final? Now I final consists of two terms. One is the inertia of the rod, the other is the inertia of this point particle, which we already learned at the beginning of the rotational part. It is mass times this distance squared. So that IF is just 1 over 12 m times b squared for the rod. This is for the rod. Plus little m times b over 2 squared for the bullet. Inertia of the rod around this midpoint, inertia of the bullet around with respect to the point O. So if you add them up, you get IF is equal to 1 over 4, 1 over 12. So 1 over 4 b squared is the common term, multiplied by capital M over 3 for the first, little m only. So this is the I final. So that L initial is L final. L initial is already found here. So that we have B mv 0 over 2 on the one hand, and this thing on the other hand, b squared over 4 multiplied by capital M over 3 plus little m. This is I. Don't forget to put this unknown omega. We want to find this omega, but there are some cancellations. Maybe these 2's will cancel, one of the b's will cancel, so that m times b0 will be b over 2 multiplied by capital M plus 3 little m divided by 3 times omega. Then it is easy to find omega. Omega is just 6mv0, 6mv0 divided by b multiplied by m plus 3m. So this is the result for angular velocity omega in the case A. But case B is the following, as the problem tells us. Now in this case, this is the fixed point O, because it can rotate around the other end, and the bullet is coming, and after the collision, it becomes such a picture. The bullet is remaining inside, and this system is moving with some other angular speed omega prime. Again by the same idea, but this time initial angular momentum is different. Now Li, what is Li? This time this is our vector r. So vector r is equal to now the full b, not half of it, but total b. So Li is initially r times p, pi. So that L initial now is total length b multiplied by m and v0 again. Not 1 over 2 is in the first case, but just b and v0. What is L final? L final now is I final times omega. But I final, now again consists of 2 parts, but the contribution from the rod is not just 1 over 12, but it is 1/3. Remember, if the rod is turning around the midpoint, it is 1 over 12 mv squared. If it is turning around the end point, it is 1/3, 4 times more. So it is on the one hand 1/3 mv squared. On the other hand, this object has a distance of b from the axis of rotation, so little m times full b squared. So it is b squared multiplied by m over 3 plus little m. Then, again from the conservation angular momentum, we have Li equals Lf, so that b times m v0 will be final inertia, which is b squared m plus 3m over 3 multiplied by the new omega prime. And these b's will cancel, and then omega prime will be 3m v0. We will compare it. 3m v0 divided by b times m plus 3m. So as you compare them, omega prime turns out to be half of omega in this case. This omega prime, because the rest is the same. M v0 over this quantity, this part is there. We have 6 or 3. So omega prime is understood to be half of omega. Now, but what is the case where the system is also moving without any obligation of staying in the same position? The system is also moving. Now also the linear momentum will be conserved. For instance, in part C, this is the case, initial case. Let's say it is moving. First of all, we have to find where the system turns around which point, since it is not fixed. This is a bit more difficult than the other cases. So what happens is the following. This is the rod, top view, of course. Top view. And we look down onto the frictionless ice surface, and the bullet is coming. Bullet is coming and hitting. And then what happens? Now assume that for simplicity, let's say masses are equal. Otherwise, it is a bit complicated for the calculation. So let's take a simple case where the bullet has the same mass as the rod. So the bullet remains inside, but then it is this case. So on the one hand, the system is moving with some velocity. Let me call it v prime. On the other hand, turning by some omega. First of all, we should find around which point the system is turning. First, we should find around which point the system is turning. And for this purpose, we use the idea of center of mass. So let's choose, for instance, along this axis, let's choose this level as r is equal to 0, for instance. So we are, first of all, wondering around which point. So this is the object, bullet, remaining at the tip of the rod, but choose this point as r equals 0, and that is the r-axis. Alright, r center of mass is, you multiply r rod mass rod, r bullet mass bullet, divided by mass rod mass bullet. But since we assume they are the same for simplicity, r center of mass, or the center of mass of the object of the system along this length, is found now. This is equal to, since the rod is uniform, we have b over 2 times the mass plus full b for the bullet, so m, and we have m plus m 2m. So m's will cancel, 1 plus 1 half, 3 halves, 3 over 4. So it corresponds to 3 quarters. If you divide it into 4 parts, this is the region, 3 over 4r. So this is the new point O. So it turns around, for instance, this is it will be the same. So the system will turn around the 3 over 4r, 3 quarters b position. So this center of mass is still the center of mass during the whole motion. At each moment, the center of mass of the system rod plus bullet will be in the same, moving on the same line. So that inertia, for instance, will be calculated with respect to that point. All right, again, Li is equal to Lf, but also Pi is equal to Pf. Again, Li is Lf, but also linear momentum will be conserved. Pi equals Pf. How can we write these equations? For instance, Pi equals Pf. Before the collision, before the bullet penetrates into the rod, we had mass, let me use all capital M and V0 for the initial linear momentum, plus the 0 for the rod because rod was at rest. After that, we have some of them moving at V prime, and therefore V prime will be 1/2 V0 over 2. This is the linear motion part of the problem. V prime is V0 over 2. First of all, this center of mass now will move at half of the speed of the bullet because we assumed they have the same mass. Otherwise, of course, in real cases, the rod is much more massive than the bullet, of course, so the final speed will be much less than the initial value V0. Alright, now what about Li-LF equation? Li, what is Li? Li is simply, now we will take this length as the R, B over 4. It is B over 4 times the momentum, linear momentum, n times V0 for the initial case. But for the final case, we have again two terms, I rod plus I bullet multiplied by omega prime, or any omega prime was used. Okay, so I rod, what is I rod? I rod is, again, it consists of two parts, 1 over 12 m times b squared for the case where it is turning around the midpoint. It is not turning around the midpoint, so we have to consider this part as the h, remember the parallel axis theorem, mh squared. So plus the additional part of m times h, but that h is also 1/4 b over 4, m times b over 4 squared for the rod, plus I bullet, it is simply m times b over 4 squared. M times b over 4 squared. So this is the sum of i's, and all multiplied by omega. The rest is simple calculations. B squared can be taken out, m can be taken out, multiplied by 1 over 12 from the first, 1 over 16 from the second, 1 over 16 from the third. So it is 1 over 8. 1 over 12 plus 1 over 8. 20 over 96. 10 over 48. 5 over 24. So it is 5 over 24 m v squared omega. That's equal to the initial value of this much. So let me write it here. Initial value b over 4 m times v0 is equal to this thing, m times b squared 5 over 24 omega. M cancel, one of the b's will cancel, this will be 6, so omega, for instance, omega will be 6 over 5 V0 over B. So this will be the final omega value with respect to the V0 and here. On the other hand, this is the linear speed of the center of mass of this combination.